Hello, it's Keith here, and this is lesson 76 of the platform-specific series of my Z80 assembly programming tutorials. And today we're looking at the Amstrad CPC, and we're going to be looking at a software tile map example. Now, the Amstrad CPC is a bitmap-based screen. It has no tile-based functionality of any kind, so this is entirely a bitmap simulation of a tile map. Now, the important thing is that this is part of the Mintile series. Mintile is a simple tile map routine which can also do simulated sprites by creating small tile maps basically, and this is a multi-platform piece of code, and it works on systems like the Amstrad CPC and the Spectrum that are bitmap based, also on systems like the Sega Master System which is tile sprite based, also on the 6502 systems like the NES which is also tile sprite based. So this is allowing us to work in a similar way on a lot of different systems. So today we're going to be looking at the Amstrad CPC version, and what we're going to see today is the code that draws the actual tiles for the screen. Now, the way Mintile works is it breaks up a tile map into a series of lines, and so what we have is a command to draw a single line of consecutive tiles from a source tile map, and there is also a version that allows for the reversing of those tiles. You can see on the screen we've got two versions of our mascot, wrong colours, but it's a mascot indeed, and this one has been horizontally flipped. Mintile supports horizontal flipping of the bitmap graphics. Mintile does not support vertical flipping. I'm working on a version called Maxtile which has more functionality. So this was the limitation of this version of the code. It does support clipping. You can see we've got the sprites moving around the screen. They can go off the screen. But to say that's basically the range of capabilities of this code. So that's what we're going to be looking at today. Okay, well, let's go over to our code and let's take a peek. So here is the file we'll be looking at today, and this is the platform-specific code. The multi-platform code is elsewhere. I've already got tutorials on that. Now, how does the drawing routine work? Well, basically we have our get screen pos function here. This is a modified version. This works in whole tiles for the vertical movement. The horizontal movement is in half tiles basically. This is because of the byte arrangement of the screen in 4-color mode. So this is used only by the sprite drawing for drawing the characters. The entire clear screen routine that redraws the entire tile map uses the screen base that is defined up here. So this is used for calculating the starting drawing position, and then the actual drawing itself is always done by this do strip routine. Now, this will draw an unflipped series of tiles to the screen. So what we're going to do basically is we have our tile map, and this is the numbered tiles, 1 byte per tile, in BC in the shadow registers. We've got the pattern data for our tiles, the bitmap patterns in DE. We have the VRAM destination, the screen memory, in HL, and we have IYL, which is the width of the tile map in this case. So that is the amount of tiles that we will be drawing to the screen. Now, our bitmap data, in this case, here it is. This is the actual tile data. So this is defined tiles. And for our Chibico mascot, there's a miniature tile map here. So tile 0, followed by tile 1, followed by tile 2, tile 3, so on. Tile 0 is effectively an unused tile. Now, in the case of a sprite, this means a part of the sprite that's transparent. In the case of the tile map, this is a tile that doesn't need to be drawn. We use a cache of changes, and so a 0 is a tile that hasn't changed, and this is how we speed up the redrawing of things to the screen. So if most of the tile map, if the tile map hasn't scrolled, most of the tile map hasn't changed, the bits where the sprite has overlapped parts might need redrawing, but other parts won't. So a 0 tile is an unused tile that shouldn't be drawn to the screen. So here is our do strip routine. Now, we're going to use stack misuse to transfer the data quickly to the screen. So we're backing up the true stack pointer here and disabling interrupts so that nothing messes with the stack. Now, we're loading C with 8 here, and this is a speed up that we'll see later on. We're then flipping into the shadow registers, and we're going to read in a tile number from BC, which is our source tile map. Now, this is the tile number. If that tile number is 0, then this is an empty tile. In the case of an empty tile, what we do is basically we skip that tile. We then move across the screen 1 byte, 1 tile effectively, and then we are decreasing our tile count and repeating if we've not reached 0 here. Now, in the case of a non-zero tile, what we're going to do is we're going to load that tile number into H here, and we're then going to set the tile within the tile map to 0 unless we've self-modified that command to do something else. We always set the tiles to 0 within the tile map for the background, but for the sprites we don't do that, and so the self-modifying code would change that to a no-op or something in the case of in the case we're drawing a sprite. What we're then going to do is we're going to take the tile number and we're going to effectively multiply that by 16 here, and we're then going to add DE to that calculated amount. This is calculating the offset of the tile number within the tile pattern data here. So that's calculating the pattern that we need to show to the screen for this tile. We're then moving to the next tile and we're moving that calculated address into the stack pointer, and what we're going to do is we're going to pop data off the stack, and that is going to be the tile pattern data that we want to transfer to the screen. Now what we're doing here is we're backing the H part up of the HL pair. We're then moving that to the accumulator, and this is so we can quickly draw our tile to the screen. What we're basically going to do is we're going to draw a byte to the screen, move across, draw a byte to the screen, move down, draw a byte to the screen, move across, draw a byte to the screen, and move down. We're basically working in a zigzag down the screen to draw the entire tile. We're then moving across and doing the next tile. That's the way I'm doing it. So we're popping 2 bytes here. We're transferring the first one to the screen, increasing L, transferring the second one to the screen, and what we're then doing is we're adding C to the accumulator and moving the accumulator into H. Now you may remember we loaded C with 8 here, and that is effectively adding hexadecimal 800 to the HL pair here, which is effectively moving down one line of the screen, provided we were within an 8x8 block. Now if we were half a tile moved down the screen, this wouldn't work, and that's why I'm limiting the Y coordinates to entire tiles. You could see that basically here, that's what that's doing here, limiting us to entire tile Y coordinates. Now Maxtile will allow you to do that. That's got more code. There's alternate versions for half tile shifts and things, but much more complicated. So there we transferred E and D to the screen, and we incremented L after the first draw. Now the second one, we're doing D followed by E, and we're decrementing L. So basically what we're doing is we're going across and then moving down and then going backwards and moving down and then going across and moving down. Reduces the amount of changes to the HL pair here. After each time we're adding C, which is 8, to the accumulator, moving the accumulator to H. This requires the accumulator to always contain the H part of the HL pair here. That's for the efficiency. So that is how we're transferring our bytes of our unflipped tile pattern to the screen. Once we're done, we're loading B back into H, effectively moving the H part of the HL pair back to the top of our tile. The L part has already been moved back to its original position, so by the time we get here, the HL pair is the same as it was at the start. Now we're going to move across one tile so that we can draw the next tile, so we're adding 2 to the L part. We don't need to change the H part because we've changed our screen size to 256 pixels wide. That is more efficient for this kind of thing, and so we don't need to change the HL part when we're moving across the screen. We're then just basically repeating until we've done our entire strip, restoring the stack pointer, and then we're returning. Now let's just very quickly have a look at the data that we're using to define that screen memory. As I say, we're using a 256 tile wide screen, whereas here it is. So these CRTC values are the correct ones for a 256 pixel by 192 screen. It's much more efficient, not just from the point of view of memory, but because that is a very common with the CPC, the Spectrum and the MSX. We can do that on a lot of systems, and so it makes our code much easier if we're working in constant settings. And so here is the code that's transferring that to the video hardware and setting up our screen. Okay, so that's how we're drawing our tiles to the screen, but we have that flipping routine, and what we're going to do is we're going to basically use the same pattern data and we're going to flip it in real time horizontally. Now there's 4 pixels per byte on a mode 1 screen, and to shift all those bits around in real time is going to be too slow. So what we're doing is we're creating a 256 byte lookup table of every possible source byte and the equivalent x-flipped version of that byte. So what we're doing here is we're calculating that lookup table. So we've got H and L, and the lookup table is aligned so that the first byte in that lookup table has the L byte of the memory address as 00. And so the L byte is effectively the value of the byte that we want to calculate the flip for. So we're loading that into the accumulator, and then what we're doing here is we're taking the 2 bits that define the leftmost pixel here, we're shifting those to the rightmost. We're then taking the next 2 and we're shifting those. We're then taking the 3rd pixel, we're shifting that, and we're taking the 4th pixel and we're shifting that. And so this has calculated the flipped equivalent of the L byte here. And so then when we're loading that into the HL address here, and we're repeating for all 256 possible bytes that we might want to flip. Well, how do we use this flipped version of our lookup table? Well, we have this alternate version of dostrip called dostrip reverse. Now what this does is it uses the lookup table, which we're loading into BC here, to calculate the flipped source byte data, and this means that we only need one set of pattern data for our normal and our flipped versions. An alternate method would be to have a flipped version of the pattern data, but that would use far more than the 256 bytes if we've got a lot of patterns, so that doesn't make sense. This is the more efficient way of dealing with it. Okay, so that's what we've got there. So most of the code here is pretty similar to before. You can see we're backing the past step pointer. We're loading in our tile number, calculating the offset within the pattern data here, and then loading that into the stack pointer here. The real difference comes within the next code. Now we have loaded in BC with the pointer to our lookup table. Now the C part of that, if we change the C byte to the byte that we've read in from our pattern and then read in from that lookup table, we will get the equivalent flipped byte, and you're going to see that's what we're doing here. So we're popping 2 bytes out of our source pattern data, and we're taking the D byte and we're loading that into the C part of the BC pair and then reading in the equivalent flipped byte of that D register there. So by loading in the accumulator there from the BC pair, after loading C with the D register, we are effectively loading in the flipped version of the value in the D register there, and then we're writing that to the screen. We're then incrementing L, and we're doing the same for the E part and writing that to the screen. Now we then want to move down one line, but because we're using B and C, we can't do anything particularly efficient here. We're also using the accumulator. So what we're doing here is we're loading in the H part, adding 8 and loading that back into H there. So that is effectively moving us down one line there. And then what we're doing here is we're doing the same again for the next pair of bytes, moving down a line, repeating, doing all of the 8 lines of our tile using that lookup table to flip the bytes there. So that's what we've done there, and that is effectively drawing us to the screen. So there we go. That's how we're doing the normal and the flipped versions of our tiles. Now both of these examples have only drawn a single line, so you're probably wondering, well, where's all the rest of the work come in? Well, that's the multi-platform code. My painfully experienced sort of lesson of all of this in multi-platform programming is make as much of your code multi-platform as possible, and there's a little platform specific, even if that often loses you efficiency, unfortunately, because you don't want to spend so long debugging your game that your game never gets finished. So a somewhat slower game that's less efficient is, if it's get finished, better than an amazingly efficient game that you never actually manage to complete. So I would recommend you try and make as much of your code multi-platform as possible if you're planning to target multiple destinations, which is why sacrificing the screen size, reducing from 320 to 256 makes sense, even if the CPC screen is capable of more, because, as I say, you just need to get the game finished in a lot of cases. Anyway, go to my website, download the source code, build scripts, all that kind of thing, and as I would say, to use the code in any way you can. Take it apart, point at it and laugh at it, whatever helps you out. So use it in anything you can, even if it's commercial. Thanks for watching today, and goodbye.